Every photograph ever taken of the surface of the sun is wrong. Not faked, not manipulated. Wrong in the quietest possible way. 3 days ago, a telescope on a mountain in Hawaii resolved the solar surface down to 19 kilometres, and the boundaries that had looked smooth in every image for 150 years turned out to be covered in whirlpools. Spinning columns of plasma, 65 kilometres apart, running along the edge of every magnetic structure in the frame. They had been there the entire time, and we simply could not see them. And the place they were hiding happens to be the exact spot where our star builds the energy it later throws at this planet. So what else have we been looking straight at and calling smooth? If that question is doing something to you, hit like and subscribe. The Skylab goes wherever the data actually leads, and drop a comment with where you're watching from, and the one thing about the sun you were taught was settled. I want to see how many of us got handed the same picture. Now let's get into it. Part 1. The blur. We mistook for a surface. For 400 years we have been looking at the sun and getting it wrong. Not wrong in the way that gets corrected by a new theory. Wrong in a much simpler and much more embarrassing way. We were looking at something that was blurry, and we didn't know it was blurry. So we wrote down what we saw and called it the surface of our star. On August 5th, 2026, that ended. A team of scientists working across 3 institutions in 2 countries published a paper in the journal Nature, and attached to that paper were images of the sun's surface at a resolution nobody had ever achieved before. And in those images was something that had been predicted by theory for more than 30 years, hunted for, never once seen, and which turned out, the moment anyone finally had a lens good enough to look, to be absolutely everywhere. Whirlpools, small, swirling, spiralling vortices, running along the edges of every magnetic structure in the field of view, churning constantly, the way the surface of a river churns where fast water slides past slow water. They had always been there. Every photograph of the sun ever taken contained them. We simply could not resolve them, and so, in every image they averaged out into a smooth grey boundary, and for a century and a half we looked at that smooth grey boundary and assumed the smoothness was real. It was not real. It was us. Now, I want to be precise about what was found here, because the difference between the accurate version and the exaggerated version of this story is the difference between something genuinely important and something that just sounds exciting. So let me give you the finding cleanly, up front, before we go anywhere near what it might mean. The images were taken with the Daniel Kea-Inouye Solar Telescope, which sits near the summit of Haleakala on the island of Maui. It has a 4-metre primary mirror. It is the largest solar telescope ever built, and that number, 4 metres, is going to matter enormously later, because it turns out to be the entire reason nobody found this until now. On the 14th of April, 2025, that telescope was pointed at a small patch of the sun containing a cluster of pores near an active region, and for a little under 3 minutes it recorded that patch at a spatial resolution of about 19 kilometres. 19 kilometres, on a star that is 1.39 million kilometres across. That is like resolving a small town on a world the size of 109 Earths lined up side by side. And at that resolution, the interfaces between the magnetic structures and the surrounding boiling plasma, the interfaces that in every previous image looked relatively smooth, slightly fuzzy, a bit indistinct, turned out to be composed, in the paper's own words, almost entirely of vortex-like structures and striations. Almost entirely. That is the finding. The place where the sun's magnetism touches the sun's convection is not a boundary. It is a churn. Here is why that matters, and I promise this is not a build-up to a disappointment. The place where the sun's magnetism meets the sun's convection is not just some interesting region. It is the specific location where the energy that powers every solar flare, every jet, every coronal mass ejection, and quite possibly the million-degree corona itself gets wound up and stored in the first place. Every model we have of how the sun stores explosive energy was built by people looking at that boundary, and that boundary was, until 3 minutes on an April afternoon last year, a blur. Let me show you the scene those images captured, because it helps to have a picture in your head before we start pulling it apart. The visible surface of the sun, the photosphere, the layer you see if you look at the sun through a proper filter, is not a solid thing. It is the top of a convection zone. Hot plasma rises from below, reaches the surface, radiates its heat away into space, cools, gets denser, and sinks back down. That process tiles the entire star with cells, called granules, each one roughly 1,000 kilometres across, each one lasting a few minutes before it dissolves and a new one takes its place. If you have ever watched a pot of thick soup just before it boils, you have seen the same pattern, bright rising cells separated by darker sinking lanes. Threaded through that boiling pattern are magnetic structures, concentrations of magnetic field, packed tight, strong enough to push back against the plasma trying to move through them. Where those concentrations get big enough, they choke off the convection entirely. The hot material cannot rise through them, so the region cools, and it appears dark. Small ones are called pores, big ones are called sunspots. That is all a sunspot is, a place where the magnetic field is winning against the boiling. So you have two things pressed against each other, across the whole magnetically active surface of the sun. Boiling plasma, moving fast and horizontally as it converges toward the sinking lanes, and magnetic structures, effectively rigid, refusing to move with it. Two fluids, different speeds, sliding past each other. If you know any fluid dynamics at all, you already know what has to happen at an interface like that, because it is one of the oldest results in the field. It happens on lakes when wind drags across still water. It happens in the atmosphere, in those beautiful rare cloud formations that look like a row of breaking ocean waves frozen in the sky. It happens in the banded atmospheres of Jupiter and Saturn. It happens where the solar wind slides along the outside of Earth's magnetic shield. Shear at an interface produces vortices. The disturbances grow, the boundary curls. It is called the Kelvin and Helmholtz instability. It was worked out in the 1860s and 1870s, and it is one of the most universal pieces of physics we have. And on the surface of our own star, in the one place where we had every theoretical reason to expect it, nobody had ever seen it. Not once. Theorists predicted it there in 1993. They refined the prediction in 2004, and for over 3 decades the observations simply were not good enough to confirm or deny it. So the prediction sat in the literature, technically unfalsified and practically untested, waiting for a lens. The paper explains the gap in a single sentence, and it is one of the most quietly devastating sentences I have read in a scientific paper this year. The existence of these instabilities in the sun's photospheric layers has not been observed in the past, it says, probably because the characteristic spatial scale is not easily accessible by telescopes with aperture sizes below 2 meters. That is it. That is the whole reason. It was not hidden. Nobody was covering it up. There was no conspiracy of silence, no suppressed data, no unpublished plates in a locked drawer. It was smaller than our telescopes. For 30 years, the answer to one of the more interesting open questions in solar physics was sitting in plain view, in daylight, on the brightest object in the sky, radiating a spectacular amount of information directly at us. And we could not read it, because our mirrors were too small. And that raises a question I want you to hold on to for the next 2 parts, because it is going to keep getting worse the deeper we go. If the smooth surface of the sun was never smooth, and the smoothness was purely an artifact of our own instruments, then what exactly have we been looking at all this time? Part 2. 3 minutes in April. The data set that changed the picture of the solar surface covers about 180 seconds. I want to sit with that for a moment, because it tells you something about how discovery actually works, and it is nothing like the version in the documentaries. There was no decade-long campaign. There was no dedicated mission with a 15-year development cycle and a mission patch. There was a telescope, a test camera, 1 target, and roughly 3 minutes of an April afternoon. The observations were acquired on the 14th of April, 2025, between 21:38 and 21:41 Universal Time. 3 minutes. The target was a region containing pores near an active region catalogued as NOAA 14060, sitting close to the centre of the visible solar disk. That last detail matters more than it sounds like it should. When you look at a point near the edge of the sun, you're looking at it obliquely, skimming across the top of the atmosphere at a shallow angle, and everything you measure is smeared along your line of sight. When you look at a point near the centre of the disk, you're looking straight down into it. The target for these observations sat at a heliocentric angle of about 14 degrees, essentially straight down. The team was looking directly into the layer they wanted to measure, not across it. Now, the conditions. This is a ground-based telescope, which means every photon it collects has to come down through the entire depth of Earth's atmosphere first, and Earth's atmosphere is a moving, turbulent, temperature-varying mess that smears starlight into a shimmering blob. That is why stars twinkle. That is also why, for most of the history of astronomy, the practical limit on resolution had nothing to do with your telescope and everything to do with the weather above it. Astronomers measure that atmospheric smearing with a number called the Fried parameter. During the best periods of this observing run, the Fried parameter was measured at around 12 centimetres. Without correction, that is roughly the effective aperture the atmosphere would have allowed. 12 centimetres of usable optical quality out of a 4-metre mirror. So the telescope was operating with its wavefront correction system in what is called diffraction-limited mode, actively measuring and correcting every optical distortion it was capable of detecting, hundreds of times per second, deforming a mirror in real time to cancel out the atmosphere. It is worth walking through what that actually involves, because it is one of the more absurd engineering achievements of the last few decades, and most people have never heard of it. Light comes down through the atmosphere and arrives at the telescope with its wavefront crumpled. The parts of it that pass through warmer, less dense air arrive slightly ahead of the parts that pass through cooler, denser air. A sensor measures the shape of that crumpling. A computer calculates the exact inverse shape, and then a deformable mirror, with hundreds of actuators pushing and pulling on its back surface, physically bends itself into that inverse shape so that when the crumpled light bounces off it, the crumples cancel out, and the wavefront comes off flat. Then it does the whole thing again, and again, hundreds of times every second, forever, for as long as you are observing. That is what the phrase diffraction-limited mode means in practice. It means the system was correcting every distortion mode it was physically capable of sensing, so that what remained was, as far as the hardware could manage, the pure diffraction limit of the mirror itself rather than the smearing of the air above it. And even that was not enough on its own. We will come to what else they had to do in the next part, because the processing chain behind these images is genuinely one of the more remarkable things in this story. But first, the camera. And this is the detail that I keep coming back to because it is so much stranger than it needs to be. The instrument that produced the highest resolution images of the sun ever recorded was not a flagship instrument. It was not the telescope's main camera. It was a diagnostic test setup built as a collaboration between the National Solar Observatory and the Max Planck Institute for Solar System Research, and it was called FastCam. It was installed in front of the entrance slit of another instrument entirely, the visible spectropolarimeter, essentially borrowing that instrument's optical path. And when the diagnostic test finished, FastCam was removed from the telescope. Read that again. The camera that produced these images was taken off the telescope when the test was over. This was, in the most literal sense, an experiment to check whether something worked. And in the process of checking whether something worked, it recorded a dynamical regime on the surface of the nearest star that no human being had ever observed. Let me give you the specifications because the numbers are worth hearing out loud. FastCam observed at 416 nanometers. That is blue continuum light, near the violet end of what your eye can see, and it is chosen deliberately. The shorter the wavelength, the finer the detail a given mirror can resolve. It used a narrow filter, half a nanometer wide, to isolate that light cleanly. The camera's pixels were 5.5 micrometers across. Through the optical setup, that translated to a scale on the sky of 0.00825 arcseconds per pixel, which corresponds to about 6 kilometers per pixel on the surface of the Sun. 6 kilometers per pixel on the Sun. The region of interest read out from the sensor was 2048 pixels by 1024, and it read that region out at 740 frames per second, with an exposure time of 100 microseconds per frame. 100 microseconds, 1/10,000th of a second per frame, 740 times every second. There is a reason for that brutal speed, and it is the atmosphere again. Atmospheric turbulence changes on timescales of a few milliseconds. If your exposure is longer than that, the distortion smears across your image and you can never remove it. If your exposure is much shorter than that, you effectively freeze the atmosphere in a single configuration. The image is still distorted, but it is distorted in one consistent way, and a consistent distortion is something you can measure and mathematically undo. You're not avoiding the problem, you're sampling it fast enough to solve it. And there was one more piece of hardware, which is the part that makes the whole thing work. The camera was fitted with a phase diversity beam splitter assembly. What that does is split the incoming light into two copies of the same field and image them side by side on the same sensor. One perfectly in focus and one deliberately defocused by about 0.4 waves. Why would you deliberately ruin one of your two images? Because comparing a focused image with a known defocused image of the same scene lets you solve backwards for exactly what distortions remain in the light after the adaptive optics has done its best. The blurry copy is not a mistake. The blurry copy is the measurement. The total field of view visible in both channels came to about 5,800 kilometres by 4,350 kilometres on the solar surface. Hold that number because it is going to become important when we get to the word ubiquitous. 5,800 by 4,350 kilometres sounds enormous. It is roughly the width of the continental United States by something like the length of it. On the Sun, it is a postage stamp. It is a patch about 0.4% of the Sun's diameter across. That is the window through which the entire boundary between magnetism and convection was seen properly for the first time. A 3-minute recording, through a test camera that got unbolted afterwards, of a patch of star the size of a country. And the raw frames coming off that sensor were still at that point unusable. Part 3. 2,000 frames for one picture. There is a sentence in the methods section of this paper that I think most people will skim straight past, and it is the single most impressive line in the entire document. The algorithm used 2,000 dark and gain calibrated camera frames to compute one reconstructed science frame. 2,000 frames for one picture. Every image you have seen from this discovery, every crisp, detailed, astonishing frame of the solar surface with those little curls of plasma running along the magnetic boundaries, is the mathematical distillate of 2,000 separate exposures, each one lasting a 10,000th of a second, each one blurred slightly differently by a slightly different configuration of Earth's atmosphere. The technique is called multi-frame blind deconvolution, and it is worth understanding what it actually does, because when we get to the part of this story where people insist these images are fake, this is the process they will be pointing at. Here is the idea. When light from the sun passes through the atmosphere applies a distortion to it. In the language of optics, that distortion is a function. You take the true image, apply the distortion function, and you get the blurred image you actually recorded. If you knew the distortion function exactly, you could apply its inverse and recover the true image. The problem is that you do not know the distortion function. It changes every few milliseconds. It is different across the field of view, and nobody hands you a copy. What blind deconvolution does is solve for both at once. Given enough frames of the same scene, each blurred differently, the algorithm looks for the single underlying true image and the set of individual distortion functions that, taken together, best explain every frame you actually recorded. The scene stays the same, the atmosphere changes. Given 2,000 samples, the shared component and the varying component can be separated, and the phase diversity setup, that deliberately defocused second copy of the field, gives the algorithm a hard constraint to work against, so it is not solving the problem purely from statistics. It is solving it with a measured reference. This is the part I want to be very direct about, because it matters for how you interpret everything that follows. This process removes distortion. It does not add detail. It is not generative. It is not a neural network hallucinating plausible-looking swirls into a fuzzy patch of sunlight. It is decades-old, published, peer-reviewed optical mathematics whose entire purpose is to subtract the atmosphere, and there is an independent check on all of it, which we will get to in Part 7, and which is honestly the most convincing part of this whole story. After reconstruction, the effective cadence of the image sequence, how often you get one finished frame, was 2.7 seconds. So from 740 raw frames per second, you end up with roughly one usable science frame every 2 and a bit seconds. That is the price. You collect an enormous flood of nearly useless data, and you crush it down into a trickle of extraordinary data, and the resolution that trickle achieved was approximately 19 kilometres. That number is not arbitrary, and it is not a target the team happened to hit. 19 kilometres is the Rayleigh diffraction limit for a 4-metre aperture at 416 nanometres. It is the hard physical floor. It is the point at which the wave nature of light itself says, no more, not with this mirror, not at this colour, not ever. They did not approach the limit. They reached it. And this is where the story acquires the quality that I find genuinely unsettling, in a way I will explain properly in the final part. When you take a measurement that runs right up against the physical limit of your instrument, you learn something real about the world. But you also learn that you have stopped learning. Whatever is smaller than 19 kilometres was in that light too. It arrived at the mirror. It was thrown away by physics before it ever reached the sensor. Alongside FastCam, 2 other instruments were watching the same scene, and they matter for a specific reason. They anchor the tiny, extraordinary view inside a normal one. The telescope's visible broadband imager took context images across a much wider field, about 50,000 kilometres by 50,000 kilometres, alternating between red continuum light at 668.4 nanometres and the hydrogen alpha line at 656.3 nanometres in sequences of 80 frames, sampled at about 12.3 kilometres per pixel and cleaned up with a different technique called speckle reconstruction. It started 3 minutes after the FastCam sequence, so it shows the same structures very slightly aged. And from orbit, the heliosysmic and magnetic imager aboard NASA's Solar Dynamics Observatory provided a full-disk view of the entire Sun at 2140 Universal Time, which was then aligned with the ground-based data by cross-correlation. Notice that the wide-field instrument used a completely different cleanup technique, speckle reconstruction rather than blind deconvolution. That is not arbitrary. Speckle methods work by taking many short exposures and statistically recovering the underlying image from the ensemble, and they scale well to large fields of view. Blind deconvolution is more computationally brutal and better suited to squeezing the absolute maximum resolution out of a small patch. Different tools, chosen for different jobs, apply to the same 3 minutes of sunlight. The wide view gives you context you could never get at maximum resolution. The narrow view gives you detail you could never get across a wide field. Neither is better. They are answering different questions, and the paper needed both, because a discovery at 19 kilometre scale is meaningless if you cannot say where on the Sun it happened. So the chain runs like this: a full disk image of the whole star, a wide field showing the active region, and then, nested inside that, a tiny window at 19 kilometre resolution showing what the boundaries in that active region are actually made of. Zoom in again, and the smooth thing dissolves into a churn. I keep returning to that because it is the spine of this entire story. The smoothness we have always seen at the interface between the Sun's magnetism and its convection was never a property of the Sun. It was a property of us. And this is not a solar physics quirk. It is a general hazard of looking at anything. Every image ever taken of anything has a resolution limit, and below that limit structure does not disappear. It averages. It becomes a shade of grey, and a shade of grey looks exactly like smoothness, which looks exactly like simplicity, which looks exactly like understanding. We have a bad habit as a species of mistaking the edge of our instruments for the edge of reality. It is not arrogance exactly. It is more that the blur is invisible as blur. There is no marker in the image that says the detail stops here. The picture simply looks finished. For a century of solar physics, the magnetic boundaries looked finished. So what did the finished picture actually turn out to contain, once someone finally had a mirror wide enough and a camera fast enough and 2,000 frames per picture? What was in the churn? Part 4. 47 whirlpools. 47. That is how many vortices the team analysed in detail in the observed field of view. Not 47 that existed, 47 that they picked out and measured properly. The paper's description of how common these things are across the boundaries is the word that ended up in the title, ubiquitous. Let me give you the measurements, because this is the heart of the discovery, and every number here is doing work. The characteristic spatial wavelength, meaning the typical distance between one vortex and the next one along a magnetic boundary, came out at 65 kilometres. The individual vortices ranged in size from 25 kilometres up to 170 kilometres across. They propagated horizontally around the edges of the magnetic elements at speeds between 0.67 and 3 kilometres per second. The upper end of that is roughly 9 times the speed of sound in Earth's air, which sounds dramatic until you remember we're talking about the surface of a star where nothing is slow. And the growth rate, this is the number that tells you how fast the instability develops, the exponential factor by which the deformation of the magnetic boundary increases over time, ran between 0.014 and 0.054 per second for the prominent examples. Turn that into something you can feel. A growth rate of 0.054 per second means the disturbance is amplifying with an e-folding time of about 18 seconds. These are not slow geological processes. A boundary perturbation that starts as an almost imperceptible ripple becomes a fully developed rolled-up vortex in well under a minute, and the whole time it is doing that, it is being carried along the edge of the magnetic structure at kilometres per second. The surface of the Sun, at the scale nobody could see, is violent and fast and constant. And then there is the number that I find genuinely difficult to think about calmly. The smallest vortices they measured sat at approximately 19 kilometres. 19 kilometres, as we established in the last part, is the diffraction limit of the telescope. It is the smallest thing a 4-metre mirror can resolve at 416 nanometres, and the smallest structures in the data are sitting exactly there. When the smallest thing you can find is precisely the smallest thing you are capable of finding, you have not measured the bottom of the distribution, you have measured the bottom of your telescope. There is almost certainly more down there. Smaller vortices, packed tighter, spinning faster. The paper cannot say how many, because there is no instrument on Earth that can look. There is no solar telescope larger than 4 meters in existence, and none under construction. So the honest summary of the smallest end of this discovery is, we found structure all the way down to the point where physics stopped us, and then we stopped. I also want to be careful about the word ubiquitous, because it is in the paper's title, and it is going to get repeated everywhere over the next few weeks, with progressively less precision attached to it. What the word describes is the field of view. Across that patch, at every interface between a magnetic flux concentration and the surrounding granulation, vortices were forming and evolving continuously, not occasionally, not at a few favoured spots. Everywhere the boundary existed, the boundary was curling. That is a strong statement, and the images support it. But the field of view was about 5,800 kilometres across, on a star 1.39 million kilometres wide, observed for 3 minutes in one active region on one day. Extrapolating from that to the whole Sun is a reasonable inference. The mechanism is generic, the ingredients are present everywhere, the field is strong enough, and there is no obvious reason this patch would be special. But it is an inference, not a survey. The honest version is that the instability is ubiquitous everywhere anyone has looked at sufficient resolution, and so far that is one place for 3 minutes, which, given that the previous count was 0 places for 0 minutes, is still an extraordinary jump. Now, that is the primary finding, and I said at the start of this video that I would give you the payoff early rather than making you wait for it. That was the payoff. Vortices everywhere, along every magnetic boundary, at sizes from 25 to 170 kilometres, spaced about 65 kilometres apart, growing in under a minute, moving at kilometres per second, extending down to the limit of what can be seen, and probably further. Everything from here deepens it, complicates it, and, in one specific case that we will get to in part 7, puts an honest crack in it that most coverage of this story is going to paper over. But before we go there, I want to spend a moment on the other thing in these images, because it solved a separate mystery almost as a side effect. Alongside the vortices, the images showed striations, fine, dark, narrow stripes, rooted in the vortices and extending outward from them, moving coherently with the swirls that spawned them. Striations at the boundaries of magnetic elements are not new. They have been showing up in high-resolution solar images for over 20 years. There is a well-known Nature paper from 2002 on dark cores in sunspot penumbral filaments. There is work from 2004 on the origin of solar faculae, and more from the same year on, how the pattern changes as you look from the centre of the Sun toward its edge. And as recently as last year, there was a dedicated paper on the dynamics of the striated solar photosphere, so the stripes were known. What was not known, observations or in simulations, and this is stated flatly in the new paper, was what physically caused the magnetic field variations that produced them. Now there is an answer. The striations arise from the Kelvin-Helmholtz instability corrugating the boundaries of the magnetic flux concentrations. The stripes are the wake of the whirlpools. And here is the detail that made me stop reading and stare at the wall for a second. The paper notes that similar magnetically induced striations are observed in molecular clouds, the vast, cold, star-forming regions of interstellar gas, structures light years across, specifically in the Polaris flare and in the Taurus clouds, where the same instability may be producing the same striated pattern. 65-kilometre stripes on the surface of a star, light-year scale stripes in a cloud of gas between stars. Same equation, same physics. Written in 1868 and 1871 by two men working on completely terrestrial problems, with no idea that the thing they had described would turn out to be one of the universe's default behaviours at every scale it operates. That's what I mean when I say the discovery here is not a new phenomenon. It is the discovery that a phenomenon we already knew was universal is also operating in the one place we had never managed to catch it, which happens to be the place where our star keeps its explosives. Because that is the part we have not touched yet. These vortices are not just interesting fluid dynamics happening in an exotic location. They are happening in a very specific place, doing a very specific thing to the magnetic field, and if the team is right about what that thing is, then these swirls are the reason the sun is able to build up the energy it later throws at us. But to explain why, I have to take you back to 1868, and to a piece of physics so simple you can demonstrate it in a bathtub. Part 5. What Kelvin and Helmholtz worked out. Hermann von Helmholtz published his analysis of discontinuous fluid motion in 1868. William Thomson, Lord Kelvin, published his hydrokinetic solutions and observations in 1871. Neither of them was thinking about stars. Helmholtz was a physician turned physicist, one of those terrifying 19th century figures who invented the ophthalmoscope, formalized the conservation of energy, and then wandered into fluid dynamics because it interested him. Kelvin was working on, among 100 other things, the problem of how wind generates waves on water. What they worked out, independently and within a few years of each other, was this. Take two layers of fluid. Have them slide past each other at different speeds. The interface between them is not stable. Any tiny disturbance on that interface, and there are always tiny disturbances, will grow. The mechanism is beautifully simple. A small bump forms on the boundary. The faster fluid has to squeeze over the bump so it accelerates. When a fluid accelerates, its pressure drops. Lower pressure above the bump means the bump gets pulled upward, which makes it bigger, which makes the fluid squeeze harder, which drops the pressure further. That is a feedback loop, and feedback loops do not gently level off. The bump grows exponentially, tips over in the direction of the flow and curls into a spiral. Then the next bump along does the same thing, and the next, until the entire boundary is a row of rolled-up vortices marching along in the direction of the shear. There is a version of this you can run yourself, and I recommend it, because holding the physical intuition makes everything that follows easier. Fill a clear container with water, add a layer of oil on top, or anything else that will not mix. Tilt it slowly so the top layer slides across the bottom one. The flat interface between them will not stay flat. It develops a row of regular waves, evenly spaced, and if you tilt it hard enough, those waves curl over at their crests into little spirals before the whole thing breaks up into a mess. That regular spacing is the important part. The waves do not appear at random intervals. There is a preferred wavelength, and it is set by the physical properties of the interface. How thick the transition between the two fluids is, how much they differ in density, how fast they are sliding. Hold on to that, because when we get back to the sun, a team is going to measure a preferred wavelength on a stellar surface and compare it against what a 19th century equation predicts. And the fact that the spacing is not random is the entire reason that comparison can be made at all. You have seen the result 1,000 times without knowing its name. It is the shape of an ocean wave breaking. It is the ripple pattern the wind draws across a wheat field. It is those rare, spectacular cloud formations that look exactly like a row of frozen surf hanging in the sky. Those are literally this instability, made visible because a layer of moist air happened to be sliding beneath a drier one at a different speed. It happens in the bands of Jupiter and Saturn, where enormous belts of atmosphere move past each other in opposite directions and their boundaries curl into the swirls you can see in any decent image of either planet. It happens in the jets of quasars. There is a famous result from 2001 identifying what the authors called a cosmic double helix in the jet of the quasar 3C273, a structure interpretable as this same instability operating on a beam of plasma being fired out of the neighbourhood of a supermassive black hole. It happens in neutron star mergers, where a 2006 paper in Science showed that this instability at the shear interface between two colliding neutron stars can amplify magnetic fields to strengths that are genuinely difficult to write down without it looking like a typo, and, this is the one that matters most for our purposes, it happens right on top of us. In 2004, a paper in Nature reported the transport of solar wind into Earth's magnetosphere through rolled-up Kelvin and Helmholtz vortices at the magnetopause. The magnetopause is the outer boundary of Earth's magnetic shield, the surface where the solar wind streaming out from the sun meets the field that protects us from it. Solar wind slides along the outside of that boundary at hundreds of kilometres per second. The plasma inside moves much more slowly. Two fluids, different speeds, sliding past each other. The boundary of Earth's magnetic shield curls into vortices, and those vortices drag solar wind plasma through a barrier that is supposed to keep it out. Later work has mapped seasonal and daily variations in how strongly this happens, and found a dawn versus dusk asymmetry in the same instability at Mercury. So consider where we had already caught this thing. We had seen it on lakes, in clouds, on Jupiter, on Saturn, at Mercury, in quasar jets, in neutron star mergers, and on the outside of our own planet's magnetic shield, where it has been quietly leaking the solar wind into our magnetosphere for as long as either has existed. What we had never seen it do was operate on the surface of the star that drives the entire system, and it is not as though nobody looked. It is not as though nobody expected it. In 1993, a team writing in the Astrophysical Journal on the formation of current sheets in the solar corona laid out the theoretical case. In 2004, a paper in Astronomy and Astrophysics on the instability in stratified shear flows sharpened it. The prediction was specific. Photospheric flows should generate velocity shear layers around magnetic flux concentrations, and those shear layers should trigger the instability. Meanwhile, elsewhere in the solar atmosphere, this instability was being found repeatedly. In 2011, observations from the Solar Dynamics Observatory reported it in the corona. In 2012, it turned up in the formation of a prominence inside a coronal cavity. In 2013, it was identified in the reconnection outflow layer of a coronal mass ejection, low in the corona. In 2016, a paper combined theory and observation to find it in chromospheric jets, and one of the authors of that 2016 paper is a joint first author on the new one. That is a researcher who has spent a decade chasing the same instability downward through the layers of the Sun's atmosphere, corona, chromosphere, and now, finally, the photosphere, the bottom, the visible surface, the layer where everything starts. The corrugated, wavy boundaries seen on coronal mass ejections have long been interpreted as possible signatures of the same physics. Possible, interpreted as. That hedged language is what solar physics had to work with for 30 years, because at the one layer where the instability would matter most, the structures were too small to resolve, and nobody could confirm anything. I keep coming back to that gap between prediction and confirmation, because it is the whole shape of this story. The churn at the magnetic boundary was not unknown, it was unseen, and those are very different failures. An unknown thing is a gap in your imagination. An unseen thing is a gap in your hardware. But knowing that shear produces vortices is not the same as knowing they will appear on the Sun, because on the Sun there is a complication, a very large one, and by rights it should have shut the whole process down. Part 6. Why the Sun could not stop it. Magnetic fields suppress turbulence. That is one of the load-bearing facts of plasma physics, and it is the reason nobody could be confident this instability would appear at the solar surface even though the shear was obviously there. The intuition is not complicated. A magnetic field threading through a conducting fluid behaves a bit like a set of elastic strings running through jelly. The plasma is stuck to the field lines and the field lines resist being bent. If you try to make the fluid curl, you have to bend the field, and bending the field costs energy and pushes back. Strong enough field and small-scale motion simply cannot get started. The magnetic flux concentrations at the solar surface are strong. stronger than what physicists call equipartition, which is the point at which the magnetic energy density matches the kinetic energy density of the plasma motion. Above that threshold, the field is winning, and the standard expectation is that turbulence gets suppressed. Equipartition is worth pausing on for a second, because it is one of those concepts that sounds technical and is actually just a fair fight. On one side, you have the kinetic energy of moving plasma, mass times velocity squared, the energy of stuff in motion. On the other, you have the energy stored in the magnetic field itself. Equipartition is the point where those two are equal. Below it, the plasma pushes the field around. Above it, the field pushes the plasma around. The magnetic elements in these regions are well above that line. The field is not merely present, it is dominant. Which is exactly why the observation is surprising. In the regime where the magnetic field is supposed to be dictating terms, the plasma found a way to curl anyway. So why did the vortices form anyway? The answer is geometry, and it comes from work Subrahmanyan Chandrasekhar published in 1961 in a book on hydrodynamic and hydromagnetic stability that is still, 6 decades later, the reference people reach for. Chandrasekhar showed that a magnetic field does not suppress this instability uniformly. It depends entirely on which way the field points relative to the shear. If the field runs parallel to the direction of the shear flow, it stabilizes the interface strongly. Your elastic strings are lying along the direction the fluid wants to curl, so any curl has to stretch them, and they resist. If the field runs perpendicular to the shear flow, it provides no stabilization at all. The strings are pointing across the motion rather than along it. The fluid can roll up without stretching anything. The magnetic field, for the purposes of this particular instability, is simply not in the way. Now look at what the Sun actually does. The magnetic flux concentrations in these regions are nearly vertical at the solar surface. The field lines come up out of the interior and point more or less straight out into space. Meanwhile, the shear that develops as granular convection slams into the side of those concentrations is horizontal. The plasma is moving sideways across the surface, converging toward the magnetic structures from all directions. Vertical field, horizontal shear. They are perpendicular. The one geometry in which the magnetic field cannot suppress the instability is precisely the geometry the Sun's surface arranges by default. The stabilizing configuration is absent, not by coincidence but by the basic architecture of how magnetoconvection works. Fields go up, flows go sideways, so the instability is free to grow in the strongest field regions on the visible surface, exactly where the standard expectation says turbulence should be dead. And the simulations let the team measure the thing the observations could not, the actual velocity field. This is one of the genuine limits of the observations. Looking down from above at 416 nanometers, you see brightness. You can watch structures move, you can measure how fast the vortices propagate along the boundary, but you cannot directly measure the horizontal plasma velocity that is driving everything. That is the ingredient the instability actually runs on, and it is invisible in the images. In the simulation, it is right there, and what it shows is a strong horizontal flow running parallel to the sharp edge of the magnetic concentration, with a steep gradient across that edge. Fast on the outside, effectively stationary on the inside with the change happening over a very short distance. That distance is the critical number, and the simulation measures it at approximately 12 kilometres. 12 kilometres. That is the thickness of the shear layer, the width of the transition zone where the plasma goes from moving at full granular speed to being locked into the magnetic structure. The reason it is that thin, incidentally, is a nice piece of physics in itself. The flow components running parallel to the interface are only weakly coupled across it. The magnetized plasma on one side and the unmagnetized plasma on the other do not share momentum efficiently. So instead of a gentle gradient spread over hundreds of kilometers, you get an almost abrupt velocity cliff. And a velocity cliff 12 kilometers wide is exactly the sort of thing that goes unstable. Now here is where it becomes satisfying, and where the case moves from suggestive to convincing. Linear theory, the mathematics that comes straight out of Chandrasekhar's treatment, says that for a shear layer of finite thickness, the fastest growing disturbance has a wavelength that scales with that thickness. Feed in a 12-kilometer shear layer, and the theory predicts that the most unstable mode should have a spatial wavelength somewhere between 60 and 100 kilometers. The observed characteristic wavelength, measured across 47 vortices in the real data, was 65 kilometers. The prediction from a 1961 textbook, fed with a shear layer thickness from a 2026 computer simulation, brackets the number measured by a telescope on a mountain in Hawaii. That is what a real confirmation looks like. Not a spectacular image that people share around. A number, predicted from independent physics, that lands inside the range where it was supposed to land. And notice how many independent steps had to line up for that to happen. Somebody had to measure the shear layer thickness in a simulation. Somebody had to solve a dispersion relation from a 1961 textbook using that thickness. Somebody else, working from telescope images, had to count vortices and find their typical spacing. Those two numbers were produced by completely different procedures, using completely different inputs, and they agree. If the underlying physics were wrong, there is no reason they would. There are a great many ways for two independent calculations to disagree, and only one way for them to match. That is the difference between a compelling picture and a result, and it means the central thread of this story now has a mechanism attached to it. The boundary between the sun's magnetism and its convection is not smooth, and the reason it is not smooth is that convection converging on a vertical field produces a 12-kilometre horizontal velocity cliff, and a 12-kilometre velocity cliff produces 65-kilometre vortices, because that is what the equations have said it would do since before anyone knew what the sun was made of. But a simulation agreeing with an observation is only impressive if the simulation was not built to agree. So how independent were these two things, actually? Part 7. The simulation that agreed. The code is called MURAM. It stands for the Max Planck Institute for Solar System Research and University of Chicago Radiative Magnetohydrodynamics Code, which is a mouthful that nobody says out loud, and it is one of the workhorse simulation tools of modern solar physics. What it does is solve the equations of magnetohydrodynamics, fluid dynamics with magnetic fields included, together with radiative transfer on a three-dimensional grid representing a chunk of the solar atmosphere. You give it initial conditions and physical constants, and you let the equations run. Nobody tells it to make vortices. Nobody tells it where the boundaries should curl. It computes what a plasma with those properties does. The setup for this study was aggressive. Because they wanted resolution comparable to the telescope, they had to shrink the simulated volume to something computationally survivable. A box roughly 6,144 kilometres on each horizontal side and about 2,000 kilometres deep. That is comparable in width to the FastCam field of view. Vertically it runs about 1,367 kilometres below the reference surface and about 681 kilometres above it. They did not start it from nothing. They took the actual magnetogram, the map of the magnetic field, that the Solar Dynamics Observatory had recorded for the very region the telescope was looking at, extracted the vertical field component, and used it to initialize the simulation. That field was enhanced by a factor of 2.5 to compensate for the dispersal that occurs when you let a simulation settle, and then the whole thing was relaxed for about 1.8 hours of simulated time, until the initial conditions stopped mattering, and the pores that formed resembled the observed ones. Then they refined the grid in stages. 4,980 seconds of simulated time at a grid spacing of 12.8 kilometres, then 1,200 seconds at 6.4 kilometres, then 1,200 seconds at 3.2 kilometres, a grid fine enough to resolve structures at roughly the same scale the telescope was resolving them. The analysed window is a slice of that finest run, the stretch between 480 and 720 seconds into it. The physics fed into it was standard, and I want to emphasise how ordinary the ingredients were, because it becomes the answer to an objection later. The simulation used 12 opacity bins, a technique for handling how radiation of different wavelengths escapes from plasma of different densities, and the Asplund 2009 solar composition, which is the widely used reference for what the sun is actually made of. No exotic physics, no tuned parameters designed to produce vortices. The same code, the same equations and the same chemical abundances that solar physicists have been running for years pushed to a finer grid than usual. There is one honest limitation the authors flag themselves. A grid spacing of 3.2 kilometres is still coarser than the real diffusive length scale in the photosphere, which they estimate at around 1.4 kilometres. Below the grid, the code has to substitute a numerical diffusivity for the real physical one. They argue that this is justified at this resolution, and they explicitly note that a properly calculated, spatially varying diffusivity would be required for any simulation finer than this one. That is what a careful paper looks like. The limitation is stated in the methods rather than left for a critic to find. And then, crucially, they did not just look at the simulation. They processed it as though it were data. They synthesized the spectrum the simulated plasma would emit across the range 415.32 to 416.7 nanometers. They computed it at a viewing angle of about 14 degrees to match where on the disk the real target sat. They passed the result through the measured transmission curve of the actual physical filter that had been in the telescope, and then they deliberately blurred the synthetic images down to decist spatial resolution, so that the simulation was handicapped to see no better than the telescope could. Only then did they measure it, using the same techniques they had used on the real images. The results from 94 instability occurrences in the synthetic data. Characteristic instability wavelength. The histogram peaked at 49 kilometres. Growth rates between 0.027 and 0.059 per second. Apparent vortex velocities between 1.6 and 2.8 kilometres per second. Now compare those against the observations. Observed velocities 0.67 to 3 kilometres per second. The synthetic range sits inside it. Observed growth rates 0.014 to 0.054 per second. The synthetic range overlaps substantially, running somewhat hotter at both ends, and observed wavelength 65 kilometres against synthetic wavelength 49 kilometres. I want to stop on that pair because this is the point where I part company slightly with how this result is being summarised. The press release describes the wavelength as ranging between 50 and 65 kilometres in both cases, which is a true statement about ranges. But the central values differ by 16 kilometres. The simulation's typical vortex spacing is about a quarter smaller than the real sun's. That is not a fatal discrepancy, and nobody is hiding it, since both numbers are printed plainly in the paper. But it is a real gap, and it is the kind of gap that usually means something. Given that the wavelength is set by the thickness of the shear layer, a systematically shorter wavelength in the simulation suggests the simulated shear layer may be slightly too thin, or that the observations are missing some of the smaller vortices which would drag the observed average upward. Both are plausible, neither is resolved, more data sets would settle it. I flag this not to undermine the result, but because you should be able to trust the numbers in a video like this, and that means telling you when two numbers that get reported as one number are actually two numbers. With that said, the overall agreement is genuinely remarkable, and the person best placed to judge it said so. Matthias Rempel of the High Altitude Observatory, one of the people who builds and maintains this code, described it this way. It is very exciting to see that the highest resolution observations of the solar photosphere revealed a new dynamical regime in the form of these vortices at the edges of magnetic field concentrations. These observations, he said, also provide the highest resolution validation of solar magnetohydrodynamic simulations to date, and the agreement in physical details is impressive. Note what he is claiming there, because it runs in two directions at once. The observations confirm the simulation. The simulation confirms the observations. Independent theory from 1961 predicts the wavelength range that both of them land in. 3 lines of evidence, developed separately, converging on the same physics. That is about as strong as confirmation gets in this field, and it is also, as we will see later, the single most effective answer to everyone who is going to insist over the next few weeks that these images are fabricated. Because you cannot fake your way into agreement with a physics code that has never seen your data. But the simulation showed the team something else, something the observations could never have revealed, and something considerably stranger than a row of surface swirls. Part 8. Rolls, not ripples. Everything I have described so far has probably left you picturing something flat. Little whirlpools skating around on the surface of the sun like leaves circling on a pond. That is not what they are. In the simulations, the vortices develop across a vertical depth range running from about 100 kilometers above the reference surface to roughly 400 kilometers below it. That is a 500-kilometer column. And across that entire column, the vortices maintain the same phase and the same wavelength. The paper's description is that they are best understood as vertically extending rolls. So the correct picture is not swirls on a surface, it is columns, tubes of rotating plasma, standing on end, running down from just above the visible surface into the star for hundreds of kilometers lined up along every magnetic boundary like a row of spinning pillars. The detail that makes this genuinely strange is that they hold their phase. Every one of those columns is rotating in step with itself from top to bottom. The vortex you see at the visible surface is the top end of a coherent structure, whose bottom end, 400 kilometres down, under enormous pressure in plasma vastly denser than the surface, is turning in the same place at the same spacing at the same moment. 400 kilometres does not sound like much next to a star. But consider what it means for the boundary. The interface between a magnetic element and the surrounding plasma is not a line drawn on a surface. It is a wall, extending downward, and that entire wall is corrugated by the same set of vertically aligned rolls. That changes what a magnetic boundary on the Sun even is. Not an edge, a fluted column, hundreds of kilometres tall, spinning along its whole length, and they get stronger as you go down. The amplitude of the perturbations and their growth rate both increase with depth. The reason is the same geometry we walked through earlier, just intensified. Deeper down, the magnetic field is even more purely vertical, and the plasma is denser, which means the plasma beta, the ratio of gas pressure to magnetic pressure, is higher. More gas pressure relative to magnetic pressure means the field has less authority over the plasma. Magnetic stabilization gets weaker with depth, so the velocity shear drives the instability more efficiently. The consequence of that is the finding in this paper I find hardest to shake. Down in those deeper layers, the instability at the magnetic boundaries does not just corrugate the edges, it fragments the structure. It splits what appears at the visible surface as a single, coherent, monolithic magnetic element into several smaller separate strands underneath. Think about what that means for how we picture these things. A pore on the surface of the Sun looks like one object. In every textbook diagram, a magnetic flux concentration is drawn as a single tube of field, rooted somewhere below and opening out into the atmosphere above. It is a clean, coherent thing. The simulations say that below the surface, that clean, coherent thing is being continuously torn into strands by an instability running along its own boundary. The single element you see is the top of a bundle that is being frayed from the outside in. The paper notes this resembles a picture Eugene Parker proposed in 1979 for much larger magnetic features, for sunspots themselves, though the mechanism he invoked there was a different instability called fluting rather than this one. So the idea that these structures are bundles rather than monoliths is not new. What is new is a specific measured process doing the bundling at a scale nobody could previously observe, and then there is the mixing. Treating the instability as a source of turbulent diffusivity, using the standard estimate, 1/3 of the typical turbulent velocity times the typical length scale, and plugging in a length scale of 65 kilometres and an average shear velocity of about 3 kilometres per second, the team arrives at a turbulent diffusivity of roughly 0.65 times 10 to the 12th square centimetres per second. The number itself will not mean much unless you work in this field. What matters is where it is happening. It is happening in regions where the magnetic field is stronger than equipartition. In other words, exactly the regions where turbulence is supposed to be suppressed. The textbook says, strong field, no mixing. The measurement says, strong field and mixing anyway, because the geometry lets the instability in through the side door, and that mixing has consequences that reach downward. It allows low entropy material from the edges of granules, cooler, denser plasma that has already given up its heat and is preparing to sink, to get inside the magnetized plasma, which changes the properties of the downflows, which changes how convective energy is transported beneath the visible surface. So the accounting on this instability keeps expanding. It corrugates the boundaries, which produces the striations. It fragments the magnetic elements into strands. It mixes magnetized and unmagnetized plasma, where mixing should not occur. It alters the downflows, and it reaches from 100 kilometers above the surface to 400 below it. There is one more behavior worth noting because it points towards something the team has not yet been able to quantify. These structures do not stay in the tidy, gentle, linear regime that the equations describe. They rapidly become nonlinear. The vortices fully roll up. They merge with each other. Smaller versions of the same instability form on the surfaces of the larger vortices, an instability growing on an instability, which the authors suggest may represent a forward turbulent cascade, energy tumbling down to ever smaller scales. And in other cases, growing vortices merge into a more turbulent state, which points toward a cascade running the other way, real turbulence generated continuously at the boundary of every magnetic structure on the Sun. It is worth unpacking what a cascade actually is, because the word gets used loosely, and the physics here is specific. In a turbulent fluid, energy injected at one scale does not stay at that scale. Large eddies break down into smaller eddies, which break down into smaller ones still, until the structures get small enough that viscosity can finally convert their motion into heat. That is a forward cascade, energy travelling downward through the scales toward dissipation. An inverse cascade runs the other way. Small structures merge into larger ones, and energy accumulates at big scales instead of small ones. It sounds counterintuitive, and in ordinary three-dimensional fluids it mostly does not happen, but in magnetized and quasi-two-dimensional systems it very much does. The paper reports signatures of both. Secondary vortices growing on the flanks of larger ones feeding energy downward, and larger vortices merging with each other, feeding it upward. Which means the magnetic boundaries on the Sun are not simply generating swirls. They are running a full turbulent energy exchange, in both directions continuously, in a region where the standard expectation was that nothing much should be happening at all. And every one of those motions is doing work on the magnetic field. Which brings us to the question that makes this discovery matter beyond the field of solar physics. Because if you have a process that is constantly everywhere, twisting and distorting the footpoints of magnetic structures, footpoints that are anchored to loops and jets and spicules reaching far up into the atmosphere above, then you may have found the answer to a question that has been open since 1972. What actually braids the Sun's magnetic field? Part 9. The Question from 1972. Eugene Parker published a paper in 1972 called Topological Dissipation and the Small-Scale Fields in Turbulent Gases. It is one of the most consequential papers in solar physics, and its central idea is easy enough to picture that you can carry it around for the rest of your life. Start with the field lines. The Sun's magnetic field emerges from the interior, arcs up through the atmosphere, and comes back down somewhere else. Where those lines pass through the visible surface, they are anchored, stuck into the plasma at what are called their foot points. Now start moving the foot points. The surface of the Sun is boiling. It is in constant convective motion. So the places where the magnetic field lines are anchored get dragged around, jostled, shuffled, rotated. And because the plasma is an excellent conductor, the field is effectively frozen into it. Move the foot point and the entire field line, arcing up through the atmosphere, has to move with it. Do that for long enough with millions of foot points moving semi-randomly, and the field lines above the surface get tangled. They wrap around each other. Parker's own analogy, and the one the National Solar Observatory used in announcing this discovery, is braiding hair. Braided field lines are not a relaxed configuration. They are a tense one. There is energy stored in that tangle, in the same way there is energy stored in a wound-up rubber band. Physicists call it free magnetic energy, and the word free is doing real work there. It means energy that is available to be released, energy the system would shed if it could find a way to unwind. The way it finds is called magnetic reconnection. Where two braided field lines are pressed hard against each other, the current density between them can climb until the plasma can no longer sustain the configuration. At that point, the field lines effectively snap and reconnect into a new, simpler topology. The tangle undoes itself locally, and the energy that was stored in the tension gets dumped all at once into heat and into the kinetic energy of accelerated particles. That is a flare. On a large scale, that is a coronal mass ejection. On a small scale, Parker proposed, that is a nanoflare, a tiny reconnection event, individually negligible, but occurring so relentlessly across the whole Sun that together they could keep the outer atmosphere hot. It is worth walking the reconnection steps slowly, because it is the moment where stored energy becomes violence, and most explanations skip straight over it. Picture two field lines running in roughly opposite directions, pushed toward each other. Between them, the field has to reverse. The region where it reverses gets compressed into a thin sheet, and a thin sheet with a field reversing across it carries an electric current. That is simply what a changing magnetic field means. Squeeze that sheet thin enough, and the plasma inside it can no longer maintain the separation. The field lines break and cross-connect. The top half of one joins the bottom half of the other. The tangle simplifies. and the newly reconnected lines, which are now sharply bent, snap outward like a released bowstring, flinging plasma away from the reconnection site at enormous speed. That snap is where the energy goes. Some becomes heat, some becomes bulk motion of the plasma, and a substantial fraction goes into accelerating individual particles to energies that let them emit X-rays, which is how we detect flares in the first place. The scale of what can be stored this way is difficult to convey. A large solar flare releases energy comparable to a substantial fraction of humanity's total annual energy consumption in minutes from a region that is small by solar standards. And all of it was sitting there beforehand, wound into the geometry of the field, put there by the slow shuffling of footpoints on the surface. So the chain of causation runs, convection moves footpoints, footpoint motion braids the field, braiding stores free magnetic energy, reconnection releases it, and the release is everything from the faintest brightening in an ultraviolet image to a coronal mass ejection large enough to knock out power grids on a planet 93 million miles away. Every link in that chain has been studied for half a century, and there has always been a weak one. The weak link is the first step, and it is worth being honest about why that step is so hard to observe, because it is not for lack of trying. To watch footpoint braiding directly, you would need to resolve the individual magnetic structures, track their motion continuously over time, and do it at a scale small enough to capture the twisting rather than just the bulk drift. Every one of those requirements fights the others. Higher resolution means a smaller field of view and less light per pixel. Longer time series means atmospheric conditions have to hold steady for longer. Smaller scales mean shorter time scales, so your cadence has to increase at the same time your light budget is collapsing. For most of the history of solar observing, you could have one or two of those things, never all three at once. So the field did what fields do when direct observation is unavailable. It inferred, it modelled the braiding statistically, it assumed a distribution of footpoint motions based on granular velocities and worked forward from there. Those models produced results that were reasonable and self-consistent, and nobody could check the assumption at the bottom of them. We know footpoint motions braid the field. We know braiding stores energy. What has never been well constrained by observation is what the footpoint motions actually are. What is the specific character of the movement? At what scale does it happen? How fast? How often? Is it random shuffling from granular convection, or is there some organized, persistent process doing the twisting? The new paper states the problem in one line. The physical drivers of braiding motions remain poorly constrained observationally. Poorly constrained observationally. That phrase is scientific for, we know it must be happening, and we cannot see it happening. And you can probably see now why a discovery about tiny vortices at the boundaries of magnetic elements is not a minor curiosity. Because what has just been observed is a process that is doing precisely this. Continuously, everywhere the magnetic field is strong enough, at the exact locations where magnetic structures meet the surface, rolling up, curling, merging, spinning at up to 3 kilometers per second, extending in columns from 100 kilometers above the surface to 400 below it, and never stopping. If you were designing a machine to braid magnetic field lines, you would design something that looked very much like this. The paper's own claim is carefully phrased, and I am going to quote it exactly rather than paraphrase it, because the precision matters. The observed vortices generated by the instability could provide an efficient source of small-scale, omnipresent magnetic flux braiding. Could provide. Not do provide. Not solve. Could provide. That is the appropriate level of confidence for a result based on 47 measured vortices in a 3-minute observation of one active region, and I would be suspicious of any coverage that upgrades that verb. But even at that level of confidence, look at what has happened here. A theoretical framework from 1972 identified a process that had to exist. A telescope in 2025 recorded a process that fits the description, and the gap between them, 53 years of knowing that something must be twisting the field and having no observation of what, has just narrowed to something you can point a camera at. Which raises a second question, and this one has a number attached to it that I find genuinely difficult to argue with. Part 10. The engine nobody could find. The sun runs on an 11-year cycle. That is such a familiar fact that it slides past without resistance. Sunspot numbers climb for about 5.5 years, peak, decline for about 5.5 years, hit a minimum, and start again. The field flips polarity along the way. Right now we're on the downslope. The sunspot number for July of 2026 came in at 78.1, down almost 48 from a year earlier. Cycle 25 is visibly winding down. Here is what nobody points out about that 11-year rhythm. 11 years is absurdly fast. The sun is 4.6 billion years old. It will keep burning for roughly another 5 billion. Against that, 11 years is not a long-term cycle. It is a flicker. The equivalent, if you scaled the sun's life to a human lifetime, of something happening several times a second. And in each of those cycles, an enormous quantity of magnetic flux gets generated by the dynamo deep inside the star, brought to the surface, and then, this is the crucial part, destroyed. It has to be destroyed. If the flux generated in one cycle survived into the next and the next and the next, it would accumulate without limit and the sun would look nothing like it does. So the magnetic field the sun produces must also be dissipated on a comparable timescale. Generation and destruction have to balance, and they have to balance fast. To see how much material has to be processed, it helps to know roughly what the dynamo is doing. Deep inside the sun, the plasma does not rotate as a solid body. The equator turns faster than the poles, and there are shear layers at depth where regions of different rotation rates grind against each other. That differential rotation takes magnetic field lines running north to south and drags them out around the star, winding them up like thread around a spindle, amplifying them enormously in the process. Convective motions then twist those wound-up bands, and buoyancy carries loops of the amplified field up to the surface, where they break through as the pairs of sunspots we see. That is the generation side, and it is efficient, extremely efficient. It converts a portion of the star's rotational energy into magnetic field, continuously, for the whole life of the star. The destruction side has to keep pace with it. Every 11 years, the entire pattern resets. The field flips its polarity, the old cycle's flux has to be cleared out, and a new one begins with the opposite sign. That clearing out is not optional bookkeeping. It is a physical requirement, and it means the sun is disposing of magnetic flux on a timescale of years, not millennia. David Kuridze, one of the two joint first authors on this paper, put the problem in a way I think is worth hearing in full. The sun's magnetic field, he said, is generated by dynamo processes that act like giant cosmic engines that turn the star's rotational energy into magnetic fields. But because the solar magnetic cycle is only 11 years, a remarkably rapid timescale in cosmic terms, the generated magnetic flux must dissipate efficiently. And then the line that matters. Current models struggle to explain this rapid diffusion. That is an admission delivered calmly inside a press release. Our models of the sun cannot destroy magnetic flux fast enough to match what the sun visibly does. There is a missing sync. Something out there is dissipating magnetic field at a rate our equations do not reproduce, and we have not known what it is. Kuridze's proposal, the Kelvin-Helmholtz instability discovered in the solar photosphere, can act as a key source of this missing magnetic diffusion. Now go back to that turbulent diffusivity number from earlier, 0.65 times 10 to the 12th square centimeters per second, generated by these vortices in regions where the magnetic field is stronger than equipartition. Remember what makes that strange. In strong field regions, turbulence is supposed to be suppressed. Suppressed turbulence means suppressed mixing. Suppressed mixing means suppressed diffusion, which means the places where the sun has the most magnetic flux to get rid of should be precisely the places where it has the least ability to get rid of it. The instability breaks that deadlock. It generates mixing inside the strong field regions, because the geometry of vertical field against horizontal shear denies the field its chance to stabilize the interface. The vortices stir magnetized and unmagnetized plasma together in exactly the locations where the textbooks say stirring should not occur. So you have a missing diffusion mechanism and a newly discovered process that generates diffusion in the specific regions where the mechanism was missing. That is not proof. Nobody has yet calculated how much of the shortfall these vortices actually account for, but it is a considerably better position than science was in a month ago, when the answer to where does all that flux go was a shrug delivered in technical language. And this is where I want to slow down and be careful, because there is a version of this video that overclaims wildly, and it would be very easy to make. Listen to how the people who did this work actually talk about it. Friedrich Vöger, senior scientist at the National Solar Observatory, and the other joint first author said, We're only at the beginning of recognizing the wide-reaching impact the discovery of this instability has on our understanding of the connection between the magnetized plasma motion and the energy transport and release into the upper solar atmosphere. Only at the beginning of recognizing. That is a scientist telling you, in the politest available phrasing, that they do not yet know how big this is. David Boboltz, the observatory's deputy director, described it as a major step forward in our understanding of the dynamics and evolution of solar and stellar plasma, and said it will serve as a basis for future discoveries. A basis for future discoveries. Also not a claim of arrival, a claim of departure. And the team has been explicit about what the next phase involves. They are building computer programs that can automatically identify and track these vortices across large volumes of data, because 47 hand-analyzed examples will not answer a quantitative question. The two things they specifically want to determine are how much energy these structures carry up into the higher atmosphere and how much they actually contribute to the spreading of magnetic fields in the lower atmosphere. Neither number exists yet. Until they do, everything in this part of the story is a strong hypothesis with a plausible mechanism attached, which is a genuinely exciting place to be and is not the same thing as an answer. But there is one more claim in this announcement that goes further than anything we have discussed. It comes from the observatory's chief technologist, and it touches a problem that predates almost everything else in this video by decades. To understand why that claim is so large, you need to know about an element that never existed. Part 11. The element that never existed. For a few minutes during a total solar eclipse, the sun's atmosphere becomes visible, not the surface. The surface is blocked by the moon, which is the whole point. What appears instead is the corona, a pale, structured, silvery halo of light streaming outward from behind the black disk, extending millions of kilometres into space, delicate enough that photographs never quite capture what the eye reports. It is the only time you can see it without specialised equipment, and for most of the history of astronomy, eclipse expeditions were the only opportunity to study it at all. Teams hauled spectroscopes onto ships and mountains and remote plains, calculated their positions to the second, and got a few minutes of data per attempt. In the 1860s, those spectroscopes found something nobody could account for. The corona's light contained bright emission lines, sharp spikes at particular wavelengths, the fingerprints atoms leave when their electrons drop between energy levels. Every element has its own pattern. Match the pattern, identify the element. That technique had just been invented and it was transforming chemistry and astronomy simultaneously. One prominent green line in the coronal spectrum matched nothing. It did not correspond to any element known on Earth. The conclusion drawn at the time was reasonable, and it had recent precedent. Helium had been identified in the Sun before it was found on Earth, spotted as an unexplained line in the solar spectrum in 1868, and not isolated terrestrially until decades later. So an unexplained line meaning a new element was not a wild leap. It was the established pattern. And you have to appreciate the circumstances under which these observations were being made, because it explains a lot about why the confusion lasted so long. An eclipse expedition in that era meant selecting a site somewhere along a track that might run through a desert, a mountain range, or a stretch of ocean. It meant transporting delicate optical instruments there by ship and cart. It meant assembling and calibrating a spectroscope in the field, often in extreme conditions, and aligning it precisely on a target that would only be visible for a couple of minutes at a moment calculated years in advance. And then it meant hoping there were no clouds. A single expedition, representing years of preparation and a substantial fraction of an observatory's budget, could yield nothing at all because of one weather system moving through at the wrong hour. The successful ones yielded perhaps 2 or 3 minutes of usable data. That is the observational base on which 19th century coronal physics was built. Minutes at a time, years apart from wherever on Earth the shadow happened to fall. It is remarkable that they extracted as much as they did, and completely unsurprising that an anomalous line went unexplained for half a century. They named the new element coronium. Coronium sat in the literature for more than half a century. It appeared in textbooks. Attempts were made to find a place for it in the periodic table. Increasingly awkward attempts because as the table filled in, the gaps where a lightweight unknown element could hide kept closing. The resolution arrived in 1939, and it did not come from finding the element. It came from realizing there was no element to find. Walter Grotrian noticed that a known transition in highly ionized iron matched one of the coronal lines, ionized meaning stripped of electrons, highly ionized meaning stripped of a great many of them. Bengt ed Len, working in the early 1940s, took that insight and did the systematic work, going through the coronal spectrum line by line and matching them to known elements in extraordinarily high ionization states. The famous green line, the one that had launched coronium in the first place, turned out to be iron. Iron that had lost 13 of its 26 electrons, half the electrons, gone. Coronium was never an element. It was ordinary iron, in a condition so extreme that nobody had thought to look for its signature there. The reason nobody had thought to look is worth explaining, because it is not an oversight. When you catalogue an element's spectral lines in a laboratory, you are working with the element in the states you can produce. Neutral iron, singly ionized iron, maybe doubly or triply, in a hot enough discharge. Those are the spectra that go into the reference tables. Iron stripped of 13 electrons is not something a 19th century laboratory could make, and for a long time it was not something a 20th century one could make easily either. The lines it emits had never been measured, because the conditions required to produce it had never been achieved on Earth. So when astronomers compared the coronal spectrum against the catalogue of known lines, the match was genuinely absent, not because the element was unknown, but because that state of a known element was. The catalogue was incomplete in a direction nobody had reason to explore, and an incomplete catalogue searched carefully and thoroughly returns the same answer as a genuinely new element, no match found, which is its own small lesson about how confident absence can be. They did the search correctly. The search was thorough. The conclusion was wrong, because the reference set had a hole in it that was invisible from the inside, and in solving one mystery, Grotrian and Edleyan created a far larger one. Because if you have identified the atoms, you have also identified the conditions required to produce them. Stripping 13 electrons off an iron atom is not gentle. Iron holds its inner electrons tightly, and each one you remove makes the next harder to take. To ionize iron to that degree, you need collisions of enormous violence, sustained across the whole region, constantly, because if the collision stopped, the ions would recombine and the lines would fade. Run the ionization calculations and they give you a temperature, not an estimate, not a guess, a requirement, 1 to 2 million Kelvin. The corona of the Sun, that faint silvery halo visible for 2 minutes during an eclipse, is at 1 to 2 million degrees. Now put that number next to the one we have been working with all video. The visible surface of the Sun, the photosphere, the layer where the vortices are, the layer that produces essentially all the light and heat that reaches Earth, sits at about 5,500 degrees. The atmosphere above the surface is hundreds of times hotter than the surface itself. Sit with that for a second, because the ordinary intuition fails completely, and it should. Walk away from a bonfire and you get cooler. Move away from a radiator and the air gets cooler. Heat flows from hot to cold. That is the second law of thermodynamics. It is one of the least negotiable facts in all of physics, and it does not have exceptions. And yet the Sun's atmosphere gets hotter as you move away from the heat source. That does not violate thermodynamics. Nothing does, but it does prove something specific and inescapable. The corona cannot be heated by the radiation coming up from the surface beneath it. That is thermodynamically forbidden. Something else must be carrying energy up there and depositing it, through a mechanism that is not simple heat flow. That question was posed in the early 1940s. It is now the mid-2020s. It is still, in its fine details, open. And on August 5th, the chief technologist of the National Solar Observatory said something about it that made me sit up. Part 12. 1,000,000 degrees above a bonfire. Thomas Rimmel's statement was this: Kelvin-Helmholtz instability is likely a mechanism that contributes to the heating of the outer atmosphere, and is part of the solution of the long-standing enigma of why stars have 1,000,000 degrees Kelvin hot corona. Read the hedges. Likely, a mechanism. Contributes, part of the solution. There are 4 separate qualifiers in a single sentence, and every one of them is load-bearing. This is not a man claiming to have solved the coronal heating problem. It is a man saying that a newly observed process is probably one of the things involved in the answer. That is still an enormous statement, and to see why, you need to know what the candidate answers have always looked like. Broadly, explanations have divided into 2 families, and they have been arguing with each other for decades. The first is wave heating. The photosphere is in constant violent motion, and motion in a magnetized plasma generates waves that travel along the field lines, the plasma equivalent of plucking a guitar string. Those waves carry energy upward. If they can be made to dissipate at the right altitude, they deposit that energy in the corona and heat it. The problem with wave heating has always been the dissipation. Waves are efficient at travelling and inefficient at stopping. Getting them to dump their energy where you need it, rather than sailing straight through, requires mechanisms whose efficiency has been argued over for a long time. The second family is nanoflare heating, which is Parker's braiding idea from Part 9 taken to its conclusion. The braided field is constantly forming small current sheets that reconnect and release energy. No individual event is significant, but if they are happening constantly, everywhere, across the whole corona, the aggregate could be enough. The problem with nanoflare heating has always been observational. Individual nanoflares are essentially by definition too small and too faint to resolve. You're inferring a population you cannot photograph. There is also a scale problem that makes the whole thing harder than it sounds. The corona is extraordinarily thin. The density up there is lower than the best vacuum most laboratories on Earth can produce. So when we say it is at 1,000,000 degrees, we are describing the energy of individual particles, not the amount of heat present. There are so few particles per cubic meter that the total thermal energy is modest. That cuts both ways. It means you do not need a colossal power supply to keep the corona hot, which makes the problem more tractable. But it also means the corona is very bad at holding on to heat. It radiates and conducts energy away continuously, so whatever is heating it has to keep working permanently without pause. You're not looking for a one-off event. You're looking for a process that never stops, which is a useful thing to have in mind when someone reports finding a process at the solar surface that appears to be running constantly, everywhere, forever. Two families of explanation, decades of argument and a shared dependency neither can escape. Both of them require something at the bottom to be doing work on the magnetic field. Waves need a driver to launch them. Braiding needs a driver to braid. Every version of coronal heating traces back to the photosphere and to the specific character of the motions happening at the foot points, which is the exact thing that has never been observed properly until now. And here is the elegant part. These vortices touch both families at once. The paper notes that the instability, by continuously distorting and perturbing magnetic elements, can excite magnetohydrodynamic waves, that is the first family, and can dissipate energy through vortices that subsequently break down into turbulence, which is a route into the second. One mechanism, two candidate solutions, both fed from the same source. I want to be very clear about what is not being claimed, because this is where the coverage over the next few weeks is going to go badly wrong. Nobody has shown that these vortices carry enough energy to heat the corona. The energy transport has not been quantified. That measurement is explicitly named as future work, and until it exists, this remains a mechanism with the right shape rather than a demonstrated cause. But the shape is right, and in a problem this old, that is not nothing. Consider the sequence. Eclipse spectroscopists in the 1860s find a green line and invent an element to explain it. Grotrian and Edlen dissolve the element in the late 1930s and early 40s and reveal a temperature nobody can account for. Parker proposes braiding in 1972 and identifies the mechanism but not its driver. Theorists predict this instability at the photosphere in 1993 and again in 2004, and cannot confirm it because their telescopes are too small. And in April of 2025, a 4-meter mirror on a mountain in Hawaii, running a test camera that was unbolted afterwards, records 3 minutes of data containing the thing they predicted. That is 160 years of one question, handed forward. I find that lineage genuinely moving, and I want to name why. Not one of the people in that chain got to see the end of it. The eclipse spectroscopists died without knowing what their green line was. Grotrian and Edlen solved the identification and immediately created a temperature problem they would not live to see resolved. Parker proposed a mechanism in 1972 whose driver would not be photographed for 53 years. The theorists who predicted this instability at the photosphere in 1993 had to wait more than 3 decades for a mirror wide enough to check their work, and the answer arrived not because anyone had a better idea, but because the glass got bigger. Every one of them handed an unfinished problem to strangers and trusted that the strangers would pick it up. And the strangers did. That is the part that gets left out of the story about how science works, in favour of the version with lone geniuses and sudden flashes. The actual mechanism is slower and much more impressive. A question survives longer than the people asking it, because each generation writes down precisely what it could not do, and the next one builds the instrument. The paper that came out on August 5th is one entry in that chain. It will not be the last one. And there is a small coincidence of timing that I cannot resist mentioning, because it closes the loop rather neatly. 4 days from now, on August 12th, a total solar eclipse crosses Europe. For a couple of minutes, along a narrow track, the moon will cover the sun and the corona will become visible to the naked eye. The same structure, seen the same way it was seen in the 1860s, when spectroscopes pointed at it and found a line that did not belong to anything. Millions of people are going to look up at a million-degree mystery that nobody has fully explained 4 days after a paper proposed part of an answer for it. Most of them will have no idea. It will simply be beautiful. And the answer, if this is the answer, was never up there in the halo at all. It was down at the bottom, at the boiling surface, in swirls 65 kilometres apart that we could not see. Which brings me to the part of this story that stops being about a discovery and starts being about the limits of what we can currently perceive. Because on the same week that we finally photographed the engine, the sun quietly demonstrated that we still cannot predict what comes out of it. Part 13, 44 minutes. Today is August 8th, 2026. 3 days after that paper went public, while the images of those vortices were still circulating, the sun ran a live demonstration of how much of this we still cannot predict. I want to walk you through it by the clock, because the timing is the story, and it only works if you have the sequence in order. All of these times are universal time, and every one of them comes from a published product of the National Oceanic and Atmospheric Administration's Space Weather Prediction Center, the agency responsible for forecasting exactly this. Quickly, on what the K-index actually is, because it gets thrown around constantly, and almost nobody explains it. It is not a measurement of the sun. It is a measurement of the ground. Magnetometer stations distributed around the world continuously record the strength and direction of Earth's magnetic field at their location. Under quiet conditions, those readings are close to steady. When charged particles from the sun interact with the magnetosphere, they drive electric currents in the upper atmosphere, and those currents produce magnetic fields of their own that the ground stations detect as a wobble in the local reading. The K-index quantifies how big that wobble is over a 3-hour window, on a scale from 0 to 9. The planetary version, KP, combines readings from stations worldwide. So when you hear that the K-index reached 5, that is not a forecast or an interpretation. It is a report that magnetometers on the surface of this planet measured the field moving by a specific amount. It is one of the more directly physical numbers in all of space weather. Instruments on the ground, watching the ground. At 9:59 in the morning, they issue a warning for a geomagnetic K-index of 4. That is routine. The K-index is a measure of disturbance in Earth's magnetic field, running from 0 to 9, and a 4 is unremarkable, enough to note, not enough to matter. At 11:36, the K-index of 4 threshold is reached. An alert goes out 4 minutes later confirming it. At 12:23 the picture changes. A warning is issued for a K-index of 5, which corresponds to G1, a minor geomagnetic storm, valid through 6 in the evening, and then, at 12:30, 7 minutes after that warning, the Space Weather Prediction Center publishes its official 3-day forecast. I am going to quote its rationale exactly, because paraphrasing would soften it, and it does not deserve to be softened. No G1, minor or greater geomagnetic storms are expected. No significant transient or recurrent solar wind features are forecast. The greatest expected 3-hour K-index for the next 3 days, 4.33, below storm level, nothing coming. At 13:14, an alert goes out. Geomagnetic K-index of 5 reached. G1 minor storm in progress. 44 minutes after the official forecast said no storm was expected, the storm was underway. At 13:36, 22 minutes after that, a further warning is issued. K-index of 6 expected, G2 moderate, valid through 6 in the evening. The alert text notes that under these conditions the aurora may be visible as far south as New York, Wisconsin and Washington state. And then, at 14:20 comes the detail that turns this from an ordinary forecast miss into something stranger. The agency's own space weather scales product, the summary display that shows current conditions, is still showing G:0. None. No storm. That is at the same moment a G2 warning is active. Two products from the same agency, both current, contradicting each other about whether a geomagnetic storm is happening. Now, before this gets away from anyone, this was a marginal event. A G1 with a G2 warning is not dangerous. Nobody's power grid was at risk. No satellites were in serious jeopardy. And if you were not looking at space weather data, you would have had no reason to notice anything at all. I am not telling you this to alarm you. I am telling you because of what it reveals about the state of the science, and because it sits so precisely alongside the discovery we have spent this video on. Because the strangest part is not the timing, it is the driver. Look at the conditions when the storm hit. Solar wind speed at 1416 was 346 kilometres per second. That is slow, genuinely slow. Strong geomagnetic storms typically arrive on solar wind running at 500 to 800 kilometres per second. This was barely above the ambient background. The north-south component of the interplanetary magnetic field, the quantity known as BZ, sat at -4 nanotesla, slightly southward. Southward is the direction that matters. When the arriving field points opposite to Earth's own, the two can connect and energy can pour in. But -4 is a nudge, not a shove. By the standard indicators, nothing about that solar wind should have produced a storm. What actually carried it was the total field strength. BT, the overall magnitude of the interplanetary magnetic field, regardless of direction, stood at 15 nanotesla, and it had peaked at 18 nanotesla at 7:52 that morning. Compare that to the baseline. The Space Weather Prediction Center's own discussion notes that the total field started the period at 2 to 4 nanotesla, so it climbed to somewhere between 4 and 9 times its background value. And during that peak, according to their own wording, the north-south component underwent an extremely brief southward deflection of -16 nanotesla, while otherwise staying within plus or -3. An extremely brief deflection, a spike, lasting a short time, 4 times deeper than anything else in the period. So the physical picture is this. A slow, unusually strongly magnetized parcel of solar wind arrived at Earth, and for a brief window its field pointed the right way to couple efficiently into our magnetosphere. It did not need speed. It had field strength and a moment of correct alignment, and that was enough to push the planet into storm conditions that nobody had forecast an hour earlier. The energy that goes into a geomagnetic storm depends on the combination of how fast the wind is moving and how strongly it is pointing south. You can arrive at a storm from either direction. Today's was the unusual route. A slow wind with an intense field, rather than a fast wind with a moderate one. And there is one more inconsistency in the numbers worth flagging, because if you go looking at the data yourself, you will notice it. Aurora hemispheric power, a measure of how much energy is being dumped into the polar regions, was sitting at 42 gigawatts in the north and 47 in the south, and was tagged in the product as quiet to unsettled. Real storm-level events typically run above 90, so one instrument says storm, another says quiet. Both are current, both are official, and neither is lying. None of which explains the actual question, which is why nobody saw it coming. The Space Weather Prediction Center is not incompetent. They have spacecraft at the first Lagrange point specifically to give warning. They have chronographs watching the sun for eruptions. They have models. The answer to why they missed it is sitting in a NASA database, in the observing notes for 6 coronal mass ejections that left the sun 4 days earlier, and it has nothing to do with anyone's competence. Part 14. The cameras were down. The Space Weather Prediction Center attributes today's disturbance to what it calls weak coronal mass ejection influences from events that left the sun on the 4th of August. So go and look at the 4th of August. NASA maintains a catalogue called the Database of Notifications, Knowledge, Information, which records solar events as analysts identify them. For August 4th, it lists 6 coronal mass ejections at 10:09, 11:23, 13:23, 2015, 2200, and 2348, all universal time. 6 eruptions in a single day is not remarkable. What is remarkable is the observing notes attached to them. I am going to read you several, because taken together they describe something that I do not think most people realize about how we watch the sun. On the 10:09 event, not clearly visible in one instrument, and there is a data gap in another instrument's imagery in real time. On the 11:23 event, the potential source is not clear. On the 13:23 event, not visible in one instrument pair in real time due to a data gap. On the 2015 event, not visible in one instrument pair in real time due to a data gap which began at 6:24 in the morning, and not seen in a second instrument in real time due to a data gap which began at 1909. On the 2200 event, obscured by the physical support structure of one instrument, blocked in another, with a third in a data gap. Read those in sequence, and the picture assembles itself. On the day these eruptions left the sun, the fleet of instruments we rely on to see them was substantially compromised. One coronagraph had a downlink gap starting at 6:24 in the morning. Another spacecraft's coronagraph went into a gap at 1909 that evening. Several of these events were caught by a single instrument, or partially, or with no identifiable source region on the solar disk at all. It also helps to understand what a chronograph is trying to do, because the difficulty is not a design flaw, it is the fundamental problem of the instrument. The sun is overwhelmingly bright. A coronal mass ejection is a diffuse cloud of plasma leaving the sun's atmosphere, and it is faint, millions of times fainter than the disk it is departing from. To photograph it, you have to block the sun itself with a physical occulting disk inside the instrument, creating an artificial eclipse, and then image the faint structure around the edge. That works, but it comes with permanent compromises. The occulting disk has to be held in place by a physical support arm, and that arm blocks part of the field of view. It is called the pylon, and it appears in the observing notes for the 2200 event on August 4th. An eruption partly obscured because it happened to leave the sun behind a piece of the instrument's own hardware. Then there is the data problem. These instruments are on spacecraft, and spacecraft downlink their data through ground stations on a schedule, with finite bandwidth. When a downlink gap occurs, the observations are not lost forever, that they usually arrive later, but they are not available in real time, which for forecasting purposes is functionally the same as not existing. A coronal mass ejection you analyse 3 days after it left is a historical record, not a warning. Now think about what a space weather forecast actually is. You cannot forecast a geomagnetic storm from Earth. By the time a coronal mass ejection reaches us, it is here. The entire forecasting enterprise depends on catching the eruption as it leaves the sun, measuring its speed and direction and apparent mass from coronagraph images, and modelling forward to predict when and whether it will arrive. The observation is the forecast. There is no other input. If you do not image the eruption properly, there is nothing to model. So the sequence that produced today's 44-minute miss looks like this. 6 coronal mass ejections leave the sun on August 4th. The coronagraph fleet is partly blind. Downlink gaps, instrument obscuration, single instrument detections, unidentified sources. The analysis produced from that incomplete imagery describes weak, poorly characterized events. 4 days later, a parcel of solar wind carrying a strong magnetic field and a brief southward deflection arrives at Earth and pushes it into storm conditions, and the forecast published at 12:30 says no significant transient solar wind features are expected, because from what could be seen 4 days earlier, that was a reasonable conclusion. That is not a failure of the forecasters, it is a failure of coverage. The models were fed a partial picture, and they returned a partial answer. And this is where it connects back to everything we have spent this video on, because the free magnetic energy that erupted from the sun on August 4th, the energy that travelled 93 million miles and disturbed the magnetic field of this planet today, came from somewhere. It came from the reservoir that footpoint braiding fills. It came, if the new paper is right, at least in part from vortices 65 kilometres apart, curling along the edges of magnetic elements, twisting field lines with every rotation for however long that region had been storing energy before it let go. So consider the week in full. On August 5th, we published the first images of the engine that may build the sun's explosive energy. On August 8th, the products of that engine arrived here, and our forecast for them was wrong by 44 minutes, because our cameras had been down when they departed. We are simultaneously seeing the sun more clearly than we ever have, and failing to see it at all. There is a useful contrast in today's data that makes the point sharper. By every other measure, the sun was quiet. The X-ray flux was sitting at B2.8, which is nearly the bottom of the scale. The strongest flare in 24 hours was a B7.6. There were no C-class flares, no M-class, no X-class, nothing at all in the categories that get anyone's attention. 5 numbered active regions were on the disk, all of them small and magnetically simple, each carrying a 1% probability of producing even a minor flare. No solar radiation storm, no radio blackout, proton flux running at roughly a 40th of the threshold that would trigger a minor alert. On paper, today was one of the least eventful solar days of the month. And the planet went into a geomagnetic storm anyway, from an eruption 4 days old that nobody had properly imaged, driven by a magnetic field enhancement rather than a fast wind, at a moment when the agency's own current conditions display was still reading 0. That is the honest state of solar forecasting in 2026. Not incompetent, not hidden. Just working with an incomplete view of a system whose critical processes have, until 3 days ago, been operating entirely below our resolution. Which brings me to the part of this I have been putting off, because the moment images like these are released, a very predictable set of claims follows them. Part 15. What people are already saying about these images. Every time a genuinely new image of something comes out, a second story forms around it within days. That story is usually not about the image, it is about trust. I want to go through the main claims properly rather than dismissing them, because a couple of them are asking reasonable questions badly, and one of them is asking a genuinely good question that deserves a real answer. The first, they finally released the real images. This has been hidden all along. This one is checkable in about 90 seconds, which is the nice thing about it. The paper is open access in Nature, meaning anyone can read the full text and methods without paying. The observatory published a downloadable media kit containing high-resolution images, video clips, and a caption document for free to anybody who wanted them. 6 named scientists across 3 institutions in 2 countries went on the record with quotes. The paper's methods section describes the instrument, the processing chain, and the limitations in enough detail that a competent researcher could attempt to replicate the analysis. That is close to the opposite of concealment, and the reason nobody had these images before is stated plainly in the paper's own text. The structures are smaller than telescopes with apertures below 2 meters can resolve. Which brings us to the second claim, and this is the interesting one. The sun is changing. This is new behavior. I understand entirely why this thought occurs. You are shown a picture of the sun that looks nothing like any picture of the sun you have seen before, and the natural inference is that the sun looks different now. But nothing in the observation supports that. The instability is the predicted consequence of ordinary granular convection, meeting ordinary magnetic flux concentrations, under conditions that have presumably held for billions of years. Theorists said it should be there in 1993. A simulation using standard physics reproduces it. There is no component of this finding that requires the sun to have changed. What changed is the resolution. And I raised this idea in yesterday's video, in a different context entirely, and it applies here so exactly that it is worth restating in one line. The rate at which we discover strange things tracks the sensitivity of our instruments far more closely than it tracks any change in the thing being observed. Every time someone switches on a better sensor, the world appears to become stranger. It did not. We did. The history of solar observation is almost a controlled experiment in this. Galileo pointed a small refractor at the sun and found spots on a body that was supposed to be perfect and unchanging. 19th century spectroscopes found lines in the corona that appeared to belong to nothing. 20th century instruments revealed granulation, then supergranulation, then the fine structure inside sunspot penumbra. Space-based telescopes found the corona to be an intricate architecture of loops rather than a smooth haze. At every single one of those steps, the sun was exactly the same star it had been the day before. And at every step, somebody could reasonably have said, "Look, it is doing something new. It never was." We just kept getting better lenses, and each new lens made the previous picture look naive in retrospect, which is precisely what this new image does to every photograph of a magnetic boundary taken before April of 2025. Third claim, this proves the electric universe. The sun is externally powered. Mainstream physics is wrong. Here the discovery is being used as evidence against the framework that predicted it, which is an unusual argumentative position. The instability is a straightforward consequence of magnetohydrodynamics, conventional plasma physics, formulated in the 1860s and 70s for ordinary fluids and extended to magnetized ones in the 20th century. And the strongest response is not rhetorical, it is the simulation. A standard radiative magnetohydrodynamics code, running conventional physics with a standard solar composition on a 3.2 kilometre grid, produced the same vortices at comparable wavelengths with comparable growth rates and comparable velocities. Nobody told it to. It computed what a magnetized plasma with those properties does. If the standard model of the solar surface were wrong in the ways that alternative frameworks require, the simulation would not have matched the photograph. The agreement between conventional theory and the new observation is not a side note, it is the refutation. Fourth, nowhere is hiding what the sun is doing and suppressing storm warnings. Today is the counterexample, and it is a good one. The forecast that said no storm was expected is public. The alert that contradicted it 44 minutes later is public. The G2 warning issued 22 minutes after that is public. The scales product that was still showing 0 at 1420 is public. Every timestamp in part 13 of this video came from documents the agency published itself, in real time, including the ones that make them look wrong. An organization suppressing information does not publish a minute-by-minute record of its own miss. Fifth, these swirls are portals, or structures, or something artificial. They are 25 to 170 kilometers across. They travel between 0.67 and 3 kilometers per second. They grow at exponential rates between 0.014 and 0.054 per second. And those numbers match what linear theory predicts from a 12-kilometer shear layer using mathematics published in 1961 that rests on work from the 1860s. A phenomenon that appears exactly where a 160-year-old equation says it should, at the size that equation predicts, growing at the rate it predicts, is the least mysterious category of discovery there is. It is only astonishing because we had never had a lens good enough to check. And the sixth, which is the one I said was a good question, the images are AI generated or artificially enhanced, so how do we know any of it is real? That deserves a serious answer rather than an eye roll because the processing is real and substantial. 2,000 raw frames go into every finished image. Blind deconvolution is genuinely reconstructing something. If you did not know what those techniques do, being suspicious would be rational. So here is the answer, in two parts. First, on what the processing does. Multi-frame blind deconvolution and phase diversity wavefront sensing are decades-old published methods whose mathematical purpose is to identify and remove atmospheric distortion. They do not add structure. They cannot invent a vortex that was not in the light, because the algorithm's job is to find the one image consistent with 2,000 differently blurred recordings of the same scene. Structure that is not present in the frames cannot survive that process. It would be inconsistent with the data. Second, and much more decisively, the simulation. A physics code that has never seen the dickest images generated the same structures from first principles. You cannot fabricate your way into agreement with an independent calculation. The photograph and the simulation are two entirely separate routes to the same answer, and they arrived at the same place. That is what makes this finding solid. Not the beauty of the image, the convergence. And with that cleared away, there is one thing left to say, and it is the part that has stayed with me since I first read the paper. Part 16. What else is still a blur? I want to end on the number 19. 19 kilometers, the resolution of these images, the Rayleigh diffraction limit of a 4-meter mirror observing at 416 nanometers. The physical flaw set by the wave nature of light itself, which no amount of processing or cleverness can push past. And the smallest vortices in the data measure approximately 19 kilometers. That is not a coincidence, and it is not a satisfying result. When the smallest thing you can find is exactly the smallest thing your instrument can detect, you have not found the bottom of anything. You have found the bottom of your telescope. There is almost certainly a population of smaller vortices below that line. The physics gives no reason for the distribution to stop conveniently at 19 kilometres. Structures at 10 kilometres, at 5, at 1, smaller, faster, more numerous, could be down there in enormous numbers, doing an unknown amount of the braiding and an unknown amount of the mixing, and none of it would appear in this data. The light carrying that information arrived at the mirror on the 14th of April, 2025. Diffraction destroyed it before it reached the sensor. To see below 19 kilometres, you would need either a shorter observing wavelength, which brings its own severe problems, or a larger aperture. And there is no solar telescope larger than 4 meters anywhere on Earth. None is under construction. The Inouye is the largest instrument of its kind that our species has ever built. It has been operating for a handful of years, and it has already run into the wall, so we are in an unusual position. We have just discovered that the interface between the sun's magnetism and its convection is far more complex than anyone knew, and simultaneously discovered that we have reached the limit of our ability to look at it. Let me put the honest ledger of this discovery in one place, so you can carry the accurate version rather than the enthusiastic one. What is established? The instability is there. It is common along magnetic boundaries. It has been measured, and a simulation reproduces it in detail. What is proposed? That these vortices are a major driver of magnetic flux braiding, that they supply the missing diffusion needed to balance an 11-year cycle, and that they contribute to heating the corona. What is unmeasured? How much energy they actually carry upward. That is the number that decides whether this is part of the coronal heating answer, or a footnote to it, and the team has named it as the next phase of work. Automated detection software, applied to far more data than 47 hand-analysed vortices. What is unresolved? The gap between the 65-kilometre wavelength in the observations and the 49-kilometre wavelength in the simulations. Somebody will explain that discrepancy eventually, and the explanation will be interesting. And what is unknown? Everything below 19 kilometres. There is a version of this story that is purely triumphant, and I understand the appeal. A 4-metre mirror on a Hawaiian mountain resolves the surface of a star and finds the machinery of solar eruptions. That is a genuinely great sentence, and it is true. But the version I keep thinking about is the uncomfortable one. For 150 years we photographed the sun. We built increasingly good instruments, and we produced increasingly detailed pictures, and we looked at the boundaries between magnetic structures and boiling plasma, and those boundaries looked smooth, not ambiguous, not obviously incomplete. Smooth, in a way that looked like a finished observation of a simple thing. They were never smooth. Every one of those images contained the churn. The vortices were in the light the whole time, arriving at every telescope every day for a century and a half, and the instruments averaged them into a soft grey edge, and we looked at the soft grey edge and believed it. That is the thing about resolution limits that I find genuinely difficult to sit with. Blur does not announce itself. There is no warning label in the corner of the image. Nothing in a smooth boundary tells you that it is smooth because you cannot see it properly. The picture simply looks complete, and so you proceed as if it is. We built models of energy storage on that boundary. We built theories of how the sun braids its field, how it dissipates its flux, how it heats an atmosphere to 1,000,000 degrees. All of it was constructed by people looking at a surface that was, at the scales that mattered most, a blur they could not identify as a blur. They were not being careless. There was no way to know. And that is the question I want to leave you with, because it is the one the whole discovery is really about, and it does not only apply to the sun. 4 days from now, on August 12th, the moon will cover the sun over Europe, and millions of people will look up at that 1,000,000-degree halo, and the process that may explain why it is hot will be invisible beneath it, 65 kilometres apart, exactly as it has been for 4.5 billion years. The people who imaged that corona in the 1860s thought they had found a new element. They had found ordinary iron under conditions they could not imagine. The people who imaged the solar surface for the next 150 years thought they had found a smooth boundary. They had found a churn they could not resolve. Both times the data was complete. Both times the interpretation was limited by the instrument, and nobody could tell from inside the picture. So here is the thread I cannot let go of, and the thing I will be watching for. The team's next step is software that finds these vortices automatically and finally measures how much energy they carry upward. the number that determines whether this explains the corona or merely decorates it. That number does not exist yet. But even when it arrives, it will be a number measured down to 19 kilometres and no further, which means the real question is not what the vortices are doing, it is what is happening at 18 kilometres and at 9 and at 2, in the light that has been arriving at every telescope on Earth every single day, carrying information we have never once been able to read and which we have spent a century and a half quietly mistaking for a smooth grey surface. What else right now are we looking straight at and calling smooth?